In this video, I'll be talking about intermolecular forces and how they're different to intramolecular forces. And you'll notice that to shorten intermolecular forces, we simply call them IMFs. So let's start with talking about bonds, all right, or attractions more specifically. So we have spent a bit of time talking about intramolecular forces. So we'll go ahead. And intramolecular forces are the forces that are the attraction between two atoms. Okay, so between atoms in a chemical. So these are attractions that happen within the actual chemical, not from one chemical to the other. And so we have been talking about the ionic bond. And the ionic bond is where we have a metal being attracted to a nonmetal. And in this case, what happens is that the electronegativity difference is so great that one of those atoms is so highly electronegative that it can actually pull the electron away from the other atom and keep it completely for itself. And so as a result, you have a positive charge and a negative charged atom. So in the case of sodium chloride, sodium has a very low electronegativity. That means it has a low tendency to be able to attract electrons, where chlorine has a high electronegativity. That means it's very likely or has a tendency to gain electrons. And so it completely strips that sodium of the one valence electron that it has and keeps it completely for itself. In this case, we call that an ionic bond, in which case the sodium and the chloride are attracted to each other because of these positive and negative charges. The other type of bond we've been talking about, and I'll go ahead and draw that down here, is a covalent bond. And in the covalent bond, we have less of a difference in electronegativity. In fact, the electrons cannot completely pull off, the atoms cannot completely pull off electrons, and instead they share the electrons. And we have two types of tug and war in this here. We have one where they're equal. That means that both chemicals have the same electronegativity or almost the same electronegativity. And so for that reason, one region is not more likely to get the electron than the other. And we had the example of oxygen bonded with another oxygen. They both have the same electronegativity because in fact they are the same chemical, and so in this case they will equally share those electrons. And we also have been talking about the hydrogen-carbon bond, where the difference is so little that we actually consider them to behave like nonpolar bonds. In this case we don't use dipoles. We've also talked about polar bonds. Polar bonds are where one chemical is more electronegative than the other. However, their difference isn't that great in electronegativity that one can pull the electron completely away from the other, but instead it pulls it closer. The more electronegative atom will pull the electron closer to it than the less electronegative atom. And so in that case, you end up having a chemical that is, here we go, a situation where the oxygen is got a higher electronegativity, and so for that reason it's more likely that that electron that they're sharing, or the electrons that they're sharing, are more on the oxygen side than on the carbon side. And that means that this area right over here is going to be more negative compared to this area. However, they still are sharing electrons, it's just that they're not sharing them equally. So these are bonds that are existing between two different atoms. So I have the bond between this oxygen and this oxygen, this carbon, this hydrogen, and this carbon and oxygen. So those are intermolecular forces. Then we have different forces that are called intermolecular forces. And intermolecular forces are the forces that chemicals experience from one molecule to the next, or one chemical to the next. So it's the attraction forces of attraction between two chemicals, okay? So now what makes this different is that intramolecular forces was the attraction between atoms, individual atoms. These are forces of attraction between two chemicals. So we're looking at a molecule being attracted to another molecule. So the first type we have is what we still consider an ionic bond. And that would be an example where we have two salt compounds attracted to each other. Okay, so we have a NaCl attracted to another NaCl. Okay, and so they would arrange themselves in this way, where we have positive and negative charges going to be attracted to each other. And these are incredibly strong bonds. And for that reason, it takes a lot of energy to actually break these ionic bonds. That is something that is unique to metals and nonmetals. In terms of molecules, remember, molecules are a situation where we have usually two nonmetals bonded together. Those are a little bit more complex. So we'll start off with one of the more easier ones. So this is specifically to molecules. We have what we call we have the nonpolar molecules. And these nonpolar molecules we call London. They experience what we call London dispersion. Write that. Forces. And the concept of these is, and let's use an oxygen attracted to another oxygen. In this case, the idea is that electrons are constantly flying around, and they are, by some freak chances, sometimes that there are more electrons in one region than there are in the other, even though they're shared equally. Because those electrons are spinning around, it's just pure chance that at some point you're going to not have them equally distributed. And then all of a sudden, within a fraction of a second, it's going to be equally distributed again. And so, for lack of better comparisons, it's sort of like these have this pulsing positive, partial positive and negative charge purely because electrons are not organized in how they fly around the nucleus, and that you can have moments, very brief moments in time where they're not equally distributed, which means that one region just for a moment is going to be partially negative and partially positive. Overall, they'll be equal in their charge distribution, but they're like these sort of pulses where they aren't. And those sort of brief moments where one region is positive and one region is negative will be able to allow the other chemicals that are experiencing the same thing be attracted to each other just for a freak second, okay? And so these are chemicals where there is not a strong attraction. It's easy to more or less break these chemicals apart from each other. They're not highly attracted to each other because the only thing that keeps them attracted to each other are these pulsating sort of moments of partial negative and partial positive charges. The next scenario is going to be the hydrogen bond. And the hydrogen bond is something that exists between polar molecules. So here we have the hydrogen bond. Okay, and in this case, it's the attraction between the hydrogen of one chemical to the nitrogen, oxygen, and fluorine of another chemical. So let's use the example of water. Here I've drawn water down here. And water we know is polar because that hydrogen-oxygen bond, there is a great difference in electronegativity, that the oxygen is going to be the more partially negative charge side of the chemical than the hydrogen. And in this case, water molecules are attracted to each other thanks to the difference in these partial charges. So in this case, the hydrogen is going to be attracted to the oxygen side of a new water molecule. And remember, this is a hydrogen to oxygen attraction, just as I said, and we call that attraction a hydrogen bond. And they are not within the chemical, but they are between two chemicals. And that was what we saw in the video of how water actually is sticky and not and doesn't come apart. And so it's this hydrogen bond that allows that to happen. And that would be the case over here as well, where we have another hydrogen being attracted to the negative side of the oxygen. Okay, so this allows water to actually be in a liquid form. The third of these intermolecular forces that you find in molecules is the dipole-dipole, which I've written in blue. And that's essentially when you have a polar bond, where, better said, a polar molecule, where we have this region being more negative to this region being attracted to another one just like itself. And so in this case, that partial negative charged oxygen is going to be attracted to the sulfur, which is partially positive, and we have the oxygens that will be coming out here. And this bond right here, or better said, I should say this attraction between this oxygen and sulfur, we call a dipole-dipole. So what makes a dipole-dipole different than a hydrogen bond? Simply which elements are involved. We do not have hydrogen involved in here, so for that reason it cannot be a hydrogen bond. A hydrogen bond is unique to having hydrogen specifically bonding with nitrogen, oxygen, or fluorine. And it has to be the hydrogen from one chemical being attracted to the oxygen and nitrogen or fluorine of another chemical. And since we don't have hydrogen here, we end up having, then in that case, what we call a dipole-dipole bond. So in terms of just the strength in these bonds, I'm going to list the strength for intermolecular forces. The strongest of these bonds in IMF bonds is definitely the ionic bond. So that would be this bond right over here. That is the strongest. It is very hard to pull these two apart, these two chemicals. The next strongest bond is going to be the hydrogen bond. That would be this one right here. They are also very strong bonds. After that, we have the dipole-dipole in terms of strength. And lastly, we have the London dispersion forces. And that would make sense in terms of London dispersion forces not being a strong bond, because remember, these are just quick moments where those positive and negative charges exist purely by just the distribution of electrons by chance. And that ends our discussion.